Yet another question. So for this question, we have a belt, a positively charged belt, something like this. So this is a two-dimensional belt, and it goes back in here. I hope you understand it. In the surface charge density of this belt is sigma, and the length, the width of the belt is L. This distance is D. Okay, and the belt is running around with velocity v. So far, so good. Inside is empty, right? So I should really draw the wheels with red, maybe.
D the radius or
D is the diameter of this. So D is this. The question is, assuming that the width and the length of the belt is much larger than D, find the magnitude and direction of the magnetic field created at the region 1 above the top part, region 2 between, and region 3 below. Like, what are the magnetic fields in these regions? Do you understand the question?
Is it plates, bent plates?
What do you mean by bent plates?
Yani bunlar ne hocam, ben tam anlayamıyorum.
It's like a conveyor belt. Do you know, like something that goes like this? So you put a package, and the package goes and someone picks. Yes? But to us, it's just current carrying planes, right? To us, that is the thing. That is,
We know the electric field, right?
the magnetic field.
No, we know the electric field, not the magnetic field.
Why do you know the electric field?
If
That's actually a good question. There is also electric field here, right? Do you know the electric field?
yes,
What is it?
sigma over 2.
Uh,
But if D is too small and we are
Yeah,
too close
Let-
to plates,
we didn't ask it, but if we asked electric field in regions 1, 2, and 3, okay, which is midterm 1 question,
yes.
right? It would be 0 inside, okay, and it would be sigma over epsilon 0 times 2, I guess, outside.
Sadece sigma olur, epsilon 0 olacak.
Mhm.
Tek plate'den sigma olursa epsilon 0 gelmez.
Yes, but you have two of them.
Bak o zaman 2 çarpı 1 bölü 2, 1.
Yes, you are right. Okay, but let's go back to magnetic field question. So what we would see if we looked from here? I always draw eyes with too much pupil, yes. So I look, there is a conveyor belt going like this, okay, and I'm looking from here. So there are currents coming towards me, currents going down away from me. All right? So currents coming out like this, going out, and that I represent with these dots, and currents going in, which I represent by these X's. Tell me, do you understand this or not?
Where is it?
So I'm looking from I'm looking from here. I'm looking from here. So currents coming out, currents going in from below. Currents coming out towards me, currents going in away from me. Okay? All right. Then let's find these currents. So this length is L. Let me just switch to this. This length is L, and this distance is D.
Are you going to use J equals in
Sort of. Okay, we are actually going to use this. We are going to use this. Yes, we are going to use Ampere's law, but let's find current. Current is, let's call it delta Q over delta T. Okay, how much delta Q do you have, for example, in this section? So in time delta T, you have V times delta T, right? And V times delta T times L is the area. So delta Q is, let me derive delta Q here. Delta Q is sigma times L times V times delta T. Does everyone get this? So sigma times the area is the charge divided by delta T. Hence, we discovered that this current coming out and going in, the magnitude of those currents are sigma times L times V. So far so good? Sigma times L times V coming out towards me, sigma times L times V going in. Okay, if I make a loop here, an Ampere's loop here, what do I see? Current coming out. By the way, I'm doing superposition. I forget about the other one. So I have a magnetic field that goes like this, right? And B dot dl is 2 times B times L. Do you agree with that?
Then why do we choose rectangular loop instead of circular one?
Because of the symmetry of the system. It's
Don't you think that is just a line?
just a line, yes. So how do you wrap around the line? With
Do we
rectangle,
have to,
right?
Cover all the line. We find near the line magnetic fields with the circle loop.
Yes, okay. You could have done it like this. That's also fine. Do you want to do it like this? I just covered all of it because we found the whole current.
Now I see my mistake then. Because the current is in that way.
Yes.
So I am thinking in that.
No. Current is coming out. That's why it's dots.
So
I put
should-
dots in here trying to say that the current is coming out of the page.
Hocam, because of that we use a rectangle, right?
Yes.
If the current would be in that.
Yes, of course. 2 times B times L should be equal to mu 0 I enclosed. Okay, mu 0 times I enclosed, and enclosed current is sigma times L times V. So, the magnetic field from one of these plates is mu 0 sigma times V over 2. But there are two of them. All right, so this one will create a magnetic field like this, but the other one, which has ingoing current, will create a magnetic field like this. And as you can see, it's independent of the distance, so there will be an arrow here as well, an arrow here as well. So outside the magnetic field will be 0. Inside they will reinforce each other, and the magnetic field in the second region will be mu 0 sigma V.
Hocam bak, we wrote 2BL already, like we multiplied with 2. Why we are multiplying again?
Very good question. So when we were doing this one, we were not thinking about that one. So, all right.
Where did that 2 come?
The 2 comes from b dot b. So b times L over here, b times L over here. Do you see? Like there is a. So let me just draw it again. So our ampere loop looks like this. B times L comes from this. B times another L comes from this. Any other questions? Is V given in this question? Do you see V? It is given. Any other questions? No questions? There was one question that you wanted me to solve. This is also from previous midterms, I guess. I wonder if I have the same question here or not. I think I don't have this particular question, so let me solve it. Circuit given below, S is open initially, the capacitor 2C has charge Q0 and the capacitor is uncharged, the switch S is closed at time 0. So I have a system like this. This is 2C, this is C, this is plus Q0 at the beginning, minus Q0 here, R, and this one starts at 0, and then the switch is closed. So far so good? What is the charge on each capacitor after a very long time? Any question? Any ideas?
I think we should calculate voltage first, then
So at infinity, after a long time has passed, what you are trying to say, I guess, is that the voltage between these 2 points should be equal to the voltage between these 2 points, because those 2 points, these 2 points are the same anyways, and these 2 points will be the same because there is no current flowing, right? So this difference is equal to that difference. All right. Then if this one has Q1, this one has Q2, Q1 over 2C is equal to Q2 over C, right? And Q1 plus Q2 needs to be Q0. Charge needs to be conserved, right? Energy is not conserved, potential energy here, because some of it will dissipate, but charge will be conserved. So Q1 times 1 plus 1/2 equals to Q0, because Q2 is half of Q1, right? So Q1 is 2 Q0 over 3, Q2 is Q0 over 3. Right. So that answers part A. Do you have any questions at this point? What is the current in the loop as a function of time for t greater than 0? What is the current in the loop? So this is a rather simple system. So we can figure out current in the loop. Okay. It's not that easy to do this. Let me think. Yeah, let's do Kirchhoff. So at any time, you have Q1 over 2C plus Q2 over C, then plus
Hocam Q2'yu Q1 cinsinden yazarsak
is this wrong?
Hocam plus, is it plus or minus IR?
İkisi yalan kaynağı.
Hocam,
It is
for the direction of the current,
it is equal to IR. Yes. What else do we need to write?
hocam Q2'ya Q1 cinsinden yazsak oradan equation'ı çözeriz gibi. Ya da birini seçip hani biri dolup biri boşalacak.
Okay.
değil mi yani işte biri boşalıyor, işaretleri aynı olmuyor.
Is there a problem?
Evet hocam.
Okay. So let me erase it. Tell me, how do you do this? So let me do this plus Q1 over here minus Q1 over here. So you are saying that this one will be plus Q2 over here minus Q2 over here, and the current is flowing this way. So let's do it properly now. So if I start from here on the left side of this one, I jump over here, and what do I have? Q1 over 2C minus IR, right? Minus Q2 over C equals to 0. Yes.
Which side is plus Q2, which
So
minus
I think it was drawn on the plot at the beginning. At the beginning, this one was plus Q0, this one was minus Q0.
Okay, but
Later on,
the other,
this one,
yes.
because so this one was charged, this one was uncharged, so the charge would start flowing here, right? It goes from plus to minus, right? So it will charge this one plus, this one minus. All right. What else do we have? We also have I equals to dq2 over dt. I is equal to dq2 over dt, which is negative of dq1 over dt.
Hocam, can you make it bigger? Please.
Yes, of course. Do you have any questions so far? Problems? So this also tells you, we also know that Q1 plus Q2 must be Q0. No. Yes. All right. So far, so good. Now we can figure it out. Q1. So let's go with Q1. Q1 over 2C minus becomes plus dQ1 over dt R minus Q0 minus Q1 over C equals to 0. Any problems at this point? No? So what do we get? 3 over 2C Q1, right? Plus dQ1 over dt R minus Q0 over C equals to 0. So let me multiply it with 2C over 3. Okay. What do I get? By the way, the person who asked this, where are you? Yes. Do you now get the 2C 2 over 3? Yes. I think that was the only problem. All right. Q1 plus dQ1 over dt times 2RC over 3. Please check my algebra. I might make a mistake. So far, how are we doing? Fine. dQ1 over, can I make some acrobatics here? Q1 minus 2Q0 over 3 equals minus dt, 3 dt over 2RC. Did I make it correctly? Yes? So I go from 0 to t, I make it t prime. I go from q0 for q1, right, to any q1 of t and make it this one, prime. So I have ln of q1 minus 2q0 over 3, and below I have q0 over 3. Then q1 is equal to 2q0 over 3 plus q0 over 3 times e to the minus 3t over 2rc. Is this the correct answer? Can you please check? Do you have the solution?
It says qt equals q0 over 3 in parentheses 1 minus e to the minus 3t over...
But that's for q2, I guess.
Hocam parantez alınca aynı şey çıkıyor bence de.
No, it's different.
Orada bir demiş burada.
Is it q2 or q1?
Q2 için diyor ya.
Yes, I think it's q2 because q2 is this one minus q2 is q0 minus q1, right? So it is indeed what you said. It is 1 minus e to the minus.
Hocam in Q2 we will set the limits of integration like 0 to Q.
Yeah.
Okay.
Yes, why not? You can't do this in the exam?
Maybe I can, but like too much computation.
Yeah.
Hocam integrale kadar gelse kaç puan?
Bence sadece bir.
I mean, if the integral is correctly constructed, you are very close to full points, right? Because coming to integral, constructing an integral correctly is, you understand it. But is it, do you mean like making a mistake on the boundaries of the integration? That's what's worrying you?
Yani tek o değil ama.
Okay. Okay. Have you seen your exam paper? No? Okay. No, I mean, like, is it because you got 100?
Hocam bir daha.
No. Okay. By the way, I know that you didn't get 100, but in any case, you would see that we are reading. I mean, whenever you have you make a mistake in part A, and you carry that mistake to part B and C, we don't take out extra points. So, yes. Any other questions? Yes.
This is not an old exam question, right?
It is an old exam question.
I couldn't find it.
Me neither. Where did you find it?
26 November
2022.
November.
November 2022.
I took this exam.
You didn't see it in the.
Obviously, I didn't
Yes.
learn it. I couldn't solve it.
Yes. Okay. I'm getting less light than before, but I'm managing. So, should we continue? The last part, I forgot. What was the last part? Let me see. What is the total energy dissipated in the resistor? So, the total energy dissipated in the resistor can be found by calculating the initial potential energy and final potential energy. Okay? Initially, the potential energy is Q0 squared over 2C. Right? In the final situation, the potential energy is, which one was 2Q? The first one was 2Q0. Squared over 2C plus Q0 over 3 squared over C, which is 2 over, no, 4. What? No, the other one is C. Okay, then I made a mistake. This one is 1/2, and this one is also 1/2. Sorry. Right? I forgot about that 1/2. Now, what do we have? 4 over 9 divided by 4, which means 1 over 9. Right? Let me change color of this part so you don't get confused. Okay. So I choose this one, take the style to something else. Now I will not be able to find that color. Sorry. Let me continue with blue. So I have 1/2 and 1 over 9. What does it give me? 1 over 18. Right? Sum them up. What do you get? 1 over 6. So you had 1 over 4 here. Now you have 1 over 6. The difference is dissipated. 1 over 6 minus 1 over 4 times Q squared over C. That's how much is dissipated. Is this correct? What does it give you? 1 over 12. Is this correct? Very good. So the next question is an easier one. So let's do this. An infinite hollow wire is used to carry current along its length. The inside of the wire is empty, while the region between the inner and outer radii is filled with a material of resistivity ρ. So this is A, this is B, this is L. There's a current running which is I, and the material is resistivity is ρ.
Hocam ağlı parti boş mu?
Yes. This part is void. Okay. What is the resistance of a section of the wire that has a length L? Do you understand the question?
Can you repeat?
What is the resistance of a section of the wire that has length L? Resistance was ρ times area over distance, right?
Hocam tam
No,
tersi değil mi?
tam tersi.
Thank you very much. So it will be ρ times big L over pi b squared over minus a squared. Do you agree with this? That's 5 easy points. Then part B asks, what is the magnitude of J of the current density within the wire?
J is I over A.
Yes. Which is?
I over, again, pi b squared minus
Yes. Another very easy 5 points. Right? Then comes the 15-point question. What is the magnitude of the magnetic field? Magnitude of the magnetic field inside this thing R. Ampere's law, yes. So here you need to figure out, of course, you are going to use Ampere's law. Integral B dot dl is B times 2 pi r. That needs to be mu 0 I enclosed. The most tricky thing here is to find I enclosed. And that's basically J times area enclosed. Right? J is I over pi b squared minus a squared, and enclosed area is pi times r squared minus a squared. So B is mu 0 over 2 pi r times I times r squared minus a squared over b squared minus a squared. Very nice question, covering several chapters. And no. How did they say in Chernobyl? Not good, not terrible.
Not so good.
Okay. Check it out, please. Yes. Okay. Any other questions? No?
Do you have any questions like solenoid or
Solenoid. Okay. Not great, not terrible.
Yani hocam gelebilitesi olası bir şey.
Everything can happen. And the ending, Mediha, the ending was, why worry about something that is never going to happen? But this is not that case. You should be worrying about something that can happen. This can happen. This is a fine question about solenoids. But we can't ask them all the way because you are not responsible from 29 and 30. They also have solenoids, right? Is this a news to you? Is this a surprise to you? It is a surprise to you. I see.
What did you say?
I said that you are not responsible from 29 and 30, and he was surprised.
John, what is 29 and
Electromagnetic induction, and what was 30? Inductance, yes. Yes, so this is a solenoid, but we don't care about its inductance. We only care about, for example, magnetic field. So in this solenoid, we have something like this. It has an inner radius, outer radius. I'm sure some of you have solved this problem. It's a solenoid wrapped around something like this. And what do we have? We know that this is very thin. Okay. We have the inner radius R1, we have outer radius R2, right? And it's tightly wound, not like I drew, it's much more tight. And it has n turns. So far, so good? Find the magnitude of the magnetic field inside this, inside and outside of the solenoid. Okay, everywhere. Find it here, and find it here. Okay? Do you understand the question? Of course, there is a current running around. There's some. Yes, thin is important here. If it's not thin, then we cannot assume that the magnetic field is uniform inside it. Am I making sense? Because you can take it all the way to this. Just imagine something like this. Then you have complications, right? Because the wire goes like this, right? And there are all kinds of complications here. But instead, we are making it very thin, which means that there is only wire going like this and going like this, so magnetic field is confined here, and outside there will be no magnetic field. Okay? That's what the difference is. So, just an application of Ampere's law. This is what it is. So at a distance r, the B dot dl is B times 2 pi r. But what is the amount of current that you are enclosing? 0, right?
where are we outside of
Inside, don't you see?
okay.
Yes. So I enclosed mu 0, I enclosed, which is 0. Hence, magnetic field for r smaller than a is r1, sorry, is 0. In between, this time we are here. Let me use different color. This time we are here. For that one, integral b dot dl is again b times 2 pi r. But how much current are we enclosing? Mu 0 n times I. So it's a different magnetic field. And outside, over here,
0 again.
0 again. That one is 0 again. That's it. This is 25 points.
Can I ask something?
Sure.
Have we ever solved a question that includes rotating objects, rotating charge objects? Because şeyi aslında dönen şeyi çözdük.
Yes, but that's not what you want. Why not? Rotating object, we can do it. We have never solved one of those. Let's do it.
Rotating object derken particle mı?
He wants a rotating object, charged rotating object, like a cylinder that is rotating, for example, right? Can we solve it?
I think
We
it-
can. Sol çözülüyor.
Let me think first. How do you solve it?
I mean, you can define a current, and then since there is a current, the magnetic field or magnetic dipole can be found.
Hocam, if we have charge Q, then current will be dq dt, and if it's rotating with omega,
Yeah. So, do you want something like this?
I don't know about the cylinder, but if it's a disk, maybe.
The cylinder
Yes. Is it okay if it's just a cylindrical shell, so that we don't bother ourselves with integration? So you just have a cylindrical shell, okay? And cylindrical shell has a sigma of charge on top of it, and it's being rotating with omega. Then the question is, of course, there are some assumptions. R is much less than L. Okay? Otherwise, there is fringing effect. Are you with me?
Yes.
Yes?
Fringing effect ne demek hocam?
Fringing is when you have something like this, so that it's not very, very long. It's not like, if it is not like this, then lots of its parts are not really uniform. So you cannot really just write down integral of b dot dl as b times l. You cannot, because most of its parts are weirdly shaped. But here, there is some fringing at the edges, but it's mostly uniform. So we assume that magnetic field is uniform throughout. All right? So the question is, okay, I gave you some R, but we are not going to use that R. We are just going to use the fact that R is much smaller than L. What is the magnetic field inside and outside of this cylinder that is rotating?
on the rotation axis to make things simple.
Yes, in the middle, right? So, what do we know? We know what we can assume is that outside the magnetic field is 0, because basically you have current going this way and current going this way, but you know by your experience that this kind of stuff don't depend on the distance. Because of that, the magnetic field generated by this current over here will cancel the magnetic field generated by this current over here. Just like the solenoid outside, I mean outside. Okay, we have seen it here, we have seen it just before over here. For example, there's a current coming out, current going in, and outside the magnetic field was 0. Similarly, outside we assume that the magnetic field is 0. We only have this amperes loop that goes like this, and there is some current going in like this. Okay? So B dot dl integral in this particular case is B times L. Just the B that comes from this B times L. Okay? And B times L must be mu 0 times I enclosed. What is I enclosed?
Sigma.
We are using R because we gave omega. Okay. We already described I as sigma times V times L. Do you remember that?
Yes.
So in this particular case, it's sigma times omega times R times L. So B times L is equal to mu 0 times sigma times omega times R times L. B is mu 0 times sigma times omega times R. Everyone is happy? Can I repeat what? The whole thing? Okay. So we have a cylindrical shell. Okay. This cylindrical shell has a sigma of charge, and when you rotate it, it's just like a solenoid having current like that. So the current comes out here, goes in here, and all these currents over here are generating magnetic field in this direction. All these currents here are generating magnetic field in that direction as well. Okay? As a result, we just assume that the magnetic field is only in this direction, uniform, inside this cylinder. Then we create a loop, Ampere's loop here, and that Ampere's loop only has this term, which is B times L. Very good question. Because there is only magnetic field here, it doesn't come out here. Ah, you are right. I made a mistake, right? While I was doing this, okay, I didn't make a mistake. Let me explain. I just put together this idea that this goes, I already used the bottom part when I took this outside B0. I already used that idea, right? That's why B times L brings me just one term.
So you conclude that you multiplied by 2.
Yes. If I didn't do that, then I would find a red magnetic field over here and magenta magnetic field, and they would cancel out over here. Both of them would be half of the size, but they would enforce each other just like before, and we would get the same result. Okay? I hope it made sense to you.
For the top one, the magnetic field in that direction. For the bottom one also. So I still think that we should multiply by 2. Like
Teneffüs zamanı.
Is it?
Isn't it?
Okay. Let's have a break.